Okay, so last time I gave you any questions before we start? Any questions about anything? Okay, so last time I put this problem up on the board. Pin joint there. Um, 500 Newton force acting at this pin. Uh, and this is an equilateral triangle, so all of these are 1 meter. You know, these are both 60 degrees. Okay, and let's put the coordinate system here. And what we want to calculate are the reactions at all three of these pins. Or another way to say it is we want to find all the external loads for each member. And this structure has only pin joints, but that's not a required property of a structure. For a structure, you just need a bunch of different members connected by joints. So we'll deal with cases with lots of different combinations of joints. So what do we want to do? The first thing is let's treat this the way we would if this were a single member and we're just trying to calculate the reaction loads at the floor, right? Like you can imagine if this pin wasn't here, we'd know how to go about this. Although, anybody see a problem? Like we wouldn't, if this wasn't a joint, we wouldn't be able to calculate the reactions here and here. You know why that is? Exactly. Yep. It's statically indeterminate because you have two variables here, and you only get three equations. But let's at least start that way. We know we can get three equations, and then let's see where we are. So first I'll isolate the whole structure. So the free body diagram looks like this. We have a force here. Oh, and let me, while we're looking at this, the whole picture, let's call this left member, member 1, and this right member, member 2. Then this reaction load here, this reaction force vector, is the force on body 1 by the ground. And this force vector is the force on body 2 by the ground. And then we still have that 500 Newton force. And so now we'll set up the table. Prepubescent athletes, row for mommy. These athletes being rowers, of course. Okay, so the our origin is right here. So let's start with this F1G. That is located at, what's the trigonometry on this? each of those sides is, okay, right. Yeah, I guess you don't need trigonometry for that, do you? So negative 0.50. Yep. And for an about point, let's choose that, negative 0.50, so we can, so at least one of these forces we're not going to have to deal with moments. Okay, so negative 0.50. Then rho is 0, 0. The force vector is F1gx, F1gy, and the moment is 0. Now this force F2g, that acts at positive 0.50. The about point is 0.5, negative 0.50, sorry. That has to be the same for all these in the same free body diagram, you know. So rho is positive 1, 0. The force is F2gx, F2gy. And so the moment is just 1 times F2gy. And then finally, where's this 500 Newton force at? Yeah, 0 sine 60, so 0.866. The about point is negative 0.50. Rho is positive 0.5, positive 0.866. The force is 500, 0. So we have 0.5 times 0 minus 500 times 0.866, and that's negative 433. And so we can write Newton's second law. Just going straight down the force column, we have F1gx, F1gy plus F2gx, F2gy plus 500, 0 equals zeros. And the rotational equation, F2gy minus 433 equals 0. Okay, so we have 4 equations, 3 equations, 4 unknowns. We can't solve it. So now what? I mean, in general, mathematically, we need more equations, or we need to decide we don't care about one of these variables. Yes, yeah, exactly. So to get more equations, we're going to just look at one of these members on its own, okay? And we're going to come up with 3 equations based on that member. The downside is, once we isolate one of these members, we expose more surface, right? Which means that we're going to most likely introduce new force variables. And it's a little unpredictable what's going to happen. Are we going to end up continuing to get more variables than we get equations at each step? Or will we eventually get the equations to catch up with the variables? You know what I mean? That's the question. I guess I wouldn't be showing you, I wouldn't be going through this example if you couldn't eventually get the equations to catch up with the variables. So feel hopeful. Okay, so we have 3 equations. Let me just write down what we have so far. We have, and I'm just rewriting these vector equations in scalar form. So we have f1gx plus f2gx is equal to negative 500. We have f1gy plus f2gy is equal to 0. And we have f2gy is equal to 433. Yep. Yep, and then you can solve for f2gy, but you can't do anything with the x's. That's right. Yep, at this point you could. I'm not going to do that yet. Think of it this way. We're trying to find a system of equations that's solvable. If you solve for the stuff you know right now, that's just you're sort of choosing how to go about solving that system. Okay, but that's kind of we don't want to miss the forest for the trees. Is that the expression? Like we're just trying to come up with a system we can solve. So let's just list out all the equations, list out all the variables, and if we can get the number of equations to catch up with the number of variables, then we'll be happy. Okay. So let's list the variables we have so far. We have f1gx, f1gy, f2gx, and f2gy. And now let's move on to body 1. And we have to be, I'll give you sort of a rule of thumb to work with after we go through all this. But for now, how are we going to treat the pin? Like there are these two bodies and then there's a pin in there. What's the deal with that? For now, let's assume that pin is its own thing. Okay? And the importance of that is body 1 and body 2 don't touch each other, right? They each touch the pin. So we're not going to have any force, you'll see, on body 1 by body 2. We're just going to have a force on body 1 by the pin. And when we isolate body 2, if we need to, I think we're going to isolate the pin instead. We'll, body 1 doesn't apply a force to body 2 either. Yep.
Where's the 500 Newton force acting on?
That's acting on the pin in this case. Yep. So that's always assumed in problems like this if you have this thing acting at the joint. Okay? You're assuming it's acting it'll normally be at a pin, or in 3D the equivalent is like at the ball in a ball and socket joint. But we'll see that the calculation would come out the same no matter where. But for now, there's really no reason for us to assume that's the case. Okay? Can someone come up with an argument that would save us a lot of work if someone could think of a reason that we don't have to treat the pin as a separate thing? Okay, now we got to do it. Okay, so we're going to keep the pins separate from body 1 and body 2. So here's the free body diagram. And what forces act on body 1? There is a force vector here, and what's this one? That's F1G, that's right. Um, we could go through the extra step of saying this pin is separate from the ground and body one, but I feel pretty comfortable with that pin just being part of the ground. Okay, so what's the force up here at the pin? That's a force on body one. What's applying that force? The pin. Okay, and what about that 500 Newton force? This is a really important point. Okay, that's right. It's applied to the pin, so it's not seen by this body. Okay, that might seem a little odd, but that's the way it has to be, and it'll turn out that when we put this system of equations together, that 500 Newton force will be reflected in the reactions by the bodies that are actually touching body one. Okay, so yeah, it's not in this free body diagram. How about pancake artists row for marzipan? I just want to give you options because that other one has some sort of weird undertones. Okay, so let's keep the coordinate system in the same spot. So this force F1G, where does that act? Yep, negative 0.50. And each body we isolate, we could put the about point in a new spot. But let's leave it right here so that, because that still eliminates one of these forces from moment calculations. So negative 0.50. Wait, is that what I did? Actually, let me do it at the other one because that's what I have in my notes. So I've already done those calculations. So let's put the about point at 0.866 for this body. Okay. There's no reason that's better or worse. It's just we're eliminating calculations for the other force. So our row vector is negative 0.5, negative 0.866. The force vector is F1G x, F1G y. And so the moment is negative 0.5 F1G y plus 0.866 F1G x. And then this force is at 0, positive 0.866. That's where the about point is. The row vector is 0, 0. The force vector, is F1px, F1py. And then that doesn't contribute any moment. So Newton's second law says F1gx, F1gy plus F1px, F1py is equal to 0, 0. And the moment equation says this expression is equal to 0. Negative 0.5 f1gy plus 0.866 f1gx is equal to 0. Okay. So let's summarize what we have now. We still have these three equations, right? Those are the first three equations of our system. Now we have three more. So I'll just number those as 4, 5, and 6. You got f1gx plus f1px is equal to 0. You got f1gy plus f1py is equal to 0. And I just rearranged these terms. Positive 0.866 f1gx minus 0.5 f1gy is equal to 0. So we have 6 equations. And how many variables do we have now? We have, okay, that's right. We have f1gx, f1gy, we have f2gx, f2gy, and we have f1px, f1py. Okay, so we have 6 variables, 6 equations. Now we have a system we can solve. We can find all those variables. There's one problem. We still don't have variables that represent all the forces we need to know the external loads on all these members. So let me say, but we still don't have the external loads for member 2 included in that list. So we still don't include all the loads on member 2. And to see that, let's look at a free body diagram of member 2. What loads are acting? Yep. Yeah, exactly. And up in this list, we don't have F2P and we don't have FP2. Okay. If we had FP2, that's just as good, because remember, the benefit of this subscript notation is that you always know that flipping the subscripts just switches the sign of the variable. Okay. So we have to do one more member, at least one more member. And I'm going to isolate the pin. So this is obviously out of scale with the other isolated members. There's something interesting about the pin. And there's sort of two ways to think about it. One is that we're treating everything as if it's acting right at this, like any loads on the pin, any forces on the pin are acting right through the center of the pin, okay? In which case nothing is going to produce a moment. We're treating it as a particle, okay? The other way to think about it is this thing is free to rotate, so we don't care about what moments are applied, okay? Either way, the conclusion is the same. We're going to do the force balance, but we're not going to do the moment balance when we isolate the pin, okay? Any questions about that? That's a way that, so anytime that you isolate a pin joint, or if you ever were to isolate like a loose ball in some kind of weird ball and socket joint, we're not going to calculate the moment equilibrium. And I'll just write that as it's free to rotate. So no rotational Newton's second law. Okay. What loads are acting on the pin? Yep. Mm-hmm. That's right. I'm going to just write it first as FP1. And then this is FP2. Okay? So Newton's second law says FP1x, FP1y plus FP2x, FP2y plus 500, 0 is equal to zeros. So that gives us equations, what are we on? 7 and 8. So equation 7 is FP1x plus FP2x is equal to negative 500. And equation 8 says FP1y plus FP2y is equal to 0. And now list the variables. F1gx, F1gy. So I'm still taking all the variables. We haven't done anything that could possibly get rid of variables we had before. So those are all in there. The question is just when we add more, okay? 2gx, 2gy. What else do we have? 1p, 1py. And then we have the new ones from these equations, FP1 and FP2. And you can hopefully see it coming that we're going to be able to reduce this list. So FP1x, FP1y, and FP2x, FP2y. And then recognize we can reduce the number of variables using Newton's third law, okay? And in order to do that, we're going to replace equation 7, or in equation 7. We're just looking through this list to see which ones are redundant based on Newton's third law. Okay, so we know this one is the same as this one, right? This one, not the same, but it gives us the same information. And then these two are new. We can't do anything with those. But so we have our new equation 7, which is negative f1px plus fp2x is equal to negative 500. And our new equation 8 says negative f1py plus fp2y is equal to 0. Okay, now we have 8 equations and 1, 2, 3, 4, 5, 6, 7, 8 variables, and we can solve it. One thing that comes up a lot in these problems is you'll finish a member and you'll have 7 variables, or say 8 variables and 9 equations. What do you think happens then? Mathematically, that can be a tricky situation, right? But for us, it doesn't matter. Any combination of those, in most cases, I'm not sure I'm ready to, I think there are times when a certain combination of those equations will be redundant and you'll have no solution. But most of the time, any combination with the right number of equations will give you the solution. And if you ever do it and don't get a solution, just try replacing one with another one, okay? It definitely won't give you any wrong information, and the equations definitely will never disagree about an answer. You know what I mean? You'll never take one combination of 8 equations and get one answer, and then take another combination of 8 equations and get a different answer. And that's really what would be the big concern, you know? Okay, so this is kind of a mess, but what are you going to do? It's the easiest way to solve it is in MATLAB. The second easiest way is on your calculator, and a distant third easiest way is to solve an 8x8 matrix equation by substitution or something by hand. So I wouldn't recommend that. So I'm just going to write out the augmented, what do they call it? Augmented matrix. So you have the 8x8 matrix with your B vector added on as like a 9th column. And I have this straight line dealie to help me. Yikes. Okay, so whoops. There's my last. That's like my B vector. And then you have this. And these matrices are always going to be quite sparse, you know, because especially the more members you have in your body, the smaller fraction of all the variables are going to act on each member. You know what I mean? So like you'll have this huge matrix in a complicated problem with just a 1 and a -1 or something over here, and then all zeros. And every row will look like that, you know? Okay, so if you just go through this list, so here's equation 1, equation 2, 3, 4, 5, 6, 7, 8. Here's your B vector of constants. And then this is the column that represents the variable f1gx, f1gy, f2gx, f2gy, f1px, f1py, fp2x, and fp2y. And you got 1, 1, and a constant of negative 500. 1, 1 here, constant of 0. 1 in the 2gy column, 433. 1gx and 1px, 0. 1gy, 1py, 0. 0.866, 1gx, and negative 0.5, 1gy, 0. And then negative 1, 1py, positive 1, oh, sorry, this should be in the 1px. So negative 1, 1px, positive 1, 2px, negative 500, and then negative 1, 1py, positive 1, 2py, 0. Solve this and you get the force F1g is equal to negative 250, negative 433, F2g is equal to negative 250, 433, F1p is equal to 250, 433, and Fp2 is negative 250, 433. Okay, let's interpret this too while we're at it. So let's look at member 1. The load's acting on that, and if you've already drawn, like when you've solved a problem like this, you've already drawn at least most of the free body diagrams. There's usually at least one member you can leave out, but you've had to do, come up with equations for most of the members. So you can look back at the free body diagram and see how these variables relate for most of them. The forces on member 1 are 1g and 1p, and we have those. So the force vector down here is negative 250, negative 433, and 1p is 250, 433. What can you tell me about that combination of forces? So they do add up to 0. So you know that, I mean, that's just the same thing as saying that they satisfy Newton's second law. They also do one more interesting thing. And this is true of any body that you ever see that's in equilibrium and all it has acting on it are two forces, okay? you call it a two-force body, and those forces have to be pointed. They have to be equal and opposite, excuse me, and they have to be pointed from one force point to the other force point. Okay, so they can both be pulling and the member's in tension, or they can both be pushing and the member's in compression. But like, think about it. If you, for this to be in static equilibrium, okay, what if you applied a force? So to satisfy Newton's second law, the forces have to be equal and opposite if you have two forces, right? But what if one force was going this way and one was going this way? It'll rotate. It wouldn't satisfy the moment equation, okay? And that's why the only way to satisfy equilibrium for a two-force body is to have a force pointed, one force pointed between the 2 points and the other one equal and opposite between the 2 points, okay? That's something we can take advantage of later when we start getting comfortable enough to cut corners, okay? Yep. Yes, that's right. They're equal and opposite, and they have the same line of action. Yep. Okay, member 2, what forces are acting on that? Oh, we didn't do that one. Well, I guess we did the free body diagram, but we didn't solve it. So the forces are F2P at the top and F2G at the bottom. We solve for F2G. So down here we know we have negative 250, positive 433. And up here, the force is F2P. We didn't solve for that one, but we solved for FP2, okay? There's FP2, so what's F2P? 250 negative 433. Which does what we just noticed it has to do. It's along the member, and it's equal and opposite to the other force. And then acting at the pin, we have, I mean, basically, like if we added up all these forces acting at the pin, what would the vector be? 0, 0, right? Because it's not going anywhere. So there's a couple ways to think about it. But I suppose I'll put all these on here. So there's that force. There's FP2. And there's FP1. We have F1P, so we have to take the negative of that, negative 250, negative 433. So add up the x's, 0, add up the y's, 0. So it's an equilibrium. Like it had to be, unless we made a mistake somewhere with our math. And this is like the next step in analyzing what's happening is the kind of thing you do in D-form. But let's just notice for a second what this is doing. Here you have a force pointing from this member up, right? Here you have a force pointing from the member down. If you apply forces out on a body like that, it puts it in tension, right? It's trying to stretch that body, okay? The other one, you have them pointing in. So it's trying to smush that body, okay? And if you look at what's happening, maybe you can sort of visualize how that works, okay? Pulling with 500 newtons over to the side, it's pulling up on this joint and stretching that member, and it's pushing down on this point and compressing that member, okay? And you start to get at that story by calculating all the external loads. Any questions on any of the steps for this? Did all the, I mean, like, it's sort of two different questions, whether you could have worked through that yourself, which maybe you don't have enough practice at doing this stuff yet to have been able to do. But hopefully you at least at each step could recognize, like, yeah, everything that we were doing made sense, you know. Nothing made me feel weird, you know. Not like that amateur rower constantly going to visit his mommy. Okay, so here's one important thing that's going to save us time in the future. Important. We treated that pin as if it was its own body. And the equivalent in 3 dimensions is like a ball. Or you also can have pins in 3D. But we don't have to. I said we and then you. We just have to be consistent about what body we want to consider the pin a part of, okay? So we're just going to assume we don't really care what's happening on the pin. The same story will be told by saying we'll always consider the pin to be part of member A, or we'll always consider the pin to be part of member, what did I say, 1 or 2, you know? We just have to be consistent. What member to lump it in with. So for example, if we decided to call the pin a part of member 1, then that 500 Newton force that was applied to the pin, we'd apply it to member 1, but we wouldn't apply it to member 2. Okay? And then we just say that the force that member 2 applies to the pin is the force that member 2 applies to member 1. Okay? Everything that we used to say happened to the pin now happens to member 1. Okay? So here's a rule of thumb. Assume the pin is part of the lowest numbered member. Okay. And maybe like if you work on problems for a while and then make this discovery that, like, oh my God, I've come up with another rule of thumb. Consider the pin to be the part of the highest numbered member. You know, that works too. You just have to be consistent, you know. So this is just a way to keep it straight in your head. Okay. So now, after kind of thinking our way through that problem just step by step, I'm going to give you a general method that you'll be able to apply to any of these structures problems. So this is a general method for structures. And before I get into the steps, I'm going to define something. And by the way, don't use this. I just made this term up, so don't use this term and expect other people to know what you're talking about. But I'm going to say I'm going to call this reducing variables. So say you're given a list of equations. Containing a list of force and couple variables. For example, you have this list. You know, the variables that appear in this list are f12x, f12y, m32, f56x, and f56y. Okay? And given a set of additional equations, for example, f21y plus m23 plus f24x equals 15. Then reducing the variables in this new set of equations means using Newton's third law to express the new equations using as many variables in the list as possible. Okay, that's just sort of like a careful way of describing what we did in that last problem. Just we're trying to use Newton's third law so we don't build up too many variables. We're trying to use as few variables as possible. Okay. So I'll call this the unreduced equation. And then in this case, let's see, what can we replace? We can replace this with this. Sorry, that's the y, right? And we can replace this one with this, and nothing else, right? So our our reduced equation then is negative f12y minus f32 plus f24x is equal to 15. So now I just defined that so that when I go through the steps of this method, I don't have, it's sort of wordy or whatever, but I can just use that idea as one of the steps that we're going to take. Anyone have any questions about that? Okay, so here's the method, and we're going to use that definition. First, number all bodies, or all members. Second, isolate the whole structure. So in your free body diagram, the reactions acting on the whole structure depend on the joints with the surroundings, right? Like in this example, when we isolated the whole structure, these reaction loads here depended on what the joints were between the ground and the whole structure. Okay. Then apply Newton's second law and the rotational Newton's second law, and that gives you 3 equations. If it's a 3D problem, everything's the same. It just gives you 6 equations, and you're just going to most likely have more variables you have to deal with. And second, list the equations and list the variables. Step 3, isolate an individual member. And here again, the reactions on these individual members are going to depend on the joints that touch that member. And also, whether you use that FAB notation and that MAB notation, when you isolate the whole thing, it isn't really crucial, because we never are, we're never going to isolate the ground, you know, so we're never going to have to reduce equations. But with these, once you start isolating the individual members, it's really crucial that you use that FAB notation. So use FAB and MAB notation. Then use Newton's second law and the rotational Newton's second law to give you 3 equations. or 6. Reduce these new equations, like following that definition I gave. And then list out all your equations and variables. And then step 4, sort of a if-else type deal. If the number of equations is greater than or equal to the number of variables, and you have all the variables you need, then just solve the system. Solve the system of equations, and you're done. Else, repeat step 3. Don't repeat it with the same member. Okay? I know some of you are going to do that. Don't act smart. Exactly. Like a day later, just like, oh, I've isolated this member 600 times and I still don't have enough equations. All right. Anybody have any questions about that? I know that was just a lot of listening passively, but next class, I think I'll do an example problem where I carefully go through those steps, and it won't be quite as long as the example I did today. And then we'll have you do a problem. We can spend a lot of time on this because it's really important. So, all right. And I need to get new practice problems to you. I'll get those up by the end of the night tonight. And then I guess we'll have to wait till Tuesday for another problem set. So, all right. Have a good weekend.